data, both structured and unstructured, there's going to be one key information or piece of knowledge. If present, we will use type A of machine learning, otherwise type B. And that key piece of information is the label information. Annotation. So this is an image of apple, that is an image of orange. If the images are labeled, we know the content or type of the image or the tweet or the review, customer review, or whatever the information we have in available. If it is labeled, then we are going to use those labels to train our algorithms. Those labels are going to supervise algorithms how to learn and what to learn. That's why when we have labels in the data, we apply algorithms that are called supervised machine learning algorithms. If we don't have labels in data, we are going to apply algorithms that are called unsupervised learning algorithms. We will start with supervised learning in this course, and we will also cover unsupervised learning methods, and then a hybrid of both. In the supervised learning methods, there are two main problems that we are going to deal with in this course. If the labels have discrete values, 0, 1, male, female, pass, fail, or some discrete values, more than 2 possibly, then we are going to do classification algorithms that learn to classify information into class A, B, C, male, female, pass, fail, 0, 1, whatever. If the labels are continuous information, continuous variable, or a number that has a range, for example, age, price, or earthquake magnitude, or whatever. If it is a number, we are going to do regression. Both regression and classification are going to be supervised learning, machine learning. Supervised, unsupervised, based on the availability of labels. Classification and regression based on the type of the label. If the label is categorical, we are doing classification. If the label is numeric and continuous variable, then regression. We are going to start with very simple machine learning technique that is used for, first we will learn how to use it for classification, and then it can also be used for regression. But you may have sensed we are starting with supervised learning methods. In this particular technique is decision trees. We are going to learn what are decision trees in the first module and how do we create algorithms that learn decision trees from data. So the task of decision tree learning is basically to given a collection of examples, let's call them X, there is a function fx when we input those x to that function, we get a mapping. That function maps x to the label of x. There could be many possible functions. We refer to them as hypotheses as well. And possibly out of many hypotheses, if we restrict our type of hypothesis to decision tree, we are going to find out the best decision tree that can provide this function hypothesis. So input to a decision tree is an object or situation that is described by a set of attributes. So when I mention attributes, that means we are talking about a structured data where we have columns and rows. Each column is an attribute. So there will be n attributes. We prepare them and do something to make them learnable put them in the format that is learnable, and they become features. So attributes of data, we transform them into features. And once that those features go into decision tree outputs a decision whether it belongs to class A or B. By it, I mean the X, the set of features. In case of decision trees, we are going to first focus on the labels that are discrete, but they can be continuous as well. When we conclude our discussion, we will know how the continuous variables can also be used in decision tree, and decision trees can do regression for us as well. But to start with, we are going to do a decision tree with Boolean classification problem, where the output or the label of the examples or objects are binary, 0, 1, positive, negative, male, female, etc. In the decision tree, we have nodes of two kinds, decision node and leaf node. In the decision nodes are the intermediate nodes in the tree that take us to the leaf of the tree. And each path or branch in the tree passes through certain decision nodes. A decision node will split our data into two or more branches. For example, we can take a decision tree as an inductive learning where we have examples and we want to find out the function, the rule. So input instance space X, we have these attributes, food, chat, fast, price, bar, and the amount of tip is the label. So big tip, yes, yes, no, yes. These are the labels for each example. Each example has 5 attributes. So the target function will map these values of the attributes, given the values of these attributes, to yes or no. There could be many possible functions. We refer to them as hypothesis space. But given the limited amount of examples, we are going to call those examples as training data to train an algorithm. Here we are talking about decision tree, using those examples and try to learn the best possible decision tree to map the values of these attributes to the binary outcome variable big tip. So in here, if we use only 3 of those attributes, F, S, P are the shorthand for the attribute names. So the feature vector x1, the vector sign here, looks like the values for f is in the first one, g for sy, for p the value is a. When we input this feature vector to the function that we are trying to learn, the output should be either 1 or 0. Given the examples that we saw on the previous slide, if we put those examples through this decision tree, the food, speed of the service, and the price, then all of these examples get correctly classified to 1 or 0. Kind of tree we are going to refer to as consistent. It's consistent with the example data. So in short, decision tree is going to represent a function that takes as input a vector x composed of the values of the attributes in the data and returns a decision y. If y can take only 2 values, we will say it's a binary classification or Boolean classification problem. Here, I'm going to throw in a few new words that we are going to use liberally in the following discussions. So the x we are going to refer to as independent variables, and the y will be referred to as dependent variable. The labels are synonymous to dependent variable, attributes, set of attributes, independent variable. So decision tree will reach to a binary decision by performing a sequence of tests, and each decision will pass through certain paths in the given decision tree. And when we reach to the leaf node will contain the decision. Each leaf node will either be 1 or 0. The strength of this kind of representation of hypothesis is that it's not a black box. We can look at it and see it's consistent with our understanding of the problem. We can look at it as how-to manuals. So, given example data, how can we learn? There could be many possible decision trees. How can we learn the best one? For example, we will look at use this example in this module where we are looking at a binary classification problem determined by these 10 attributes, where we have alternate restaurant, bar, Friday, Saturday, hungry, patrons, price, raining, reservation type, weight estimate. These attributes are given, and we want to estimate whether, given the value of each attribute, the person waiting in line outside the restaurant will keep waiting or move on to the next restaurant. So the dependent variable here is will wait, which is a binary variable. Independent variables are these 10. Notice we don't have restaurant name in the independent variables. There could be many reasons. If we know the restaurant name, well, sometimes restaurant name determines whether people will stay or move on. If it's a so-so restaurant, people will just move on. But if it is someplace exotic, people would try to wait. So given the restaurant name will have some implications on learning problem. We are going to notice, take a note here that restaurant name is missing, and we will find out why an attribute kind of restaurant name is good or not good for learning problems. First hint is that if we include restaurant name in learning problem, it won't generalize well. We want to make a decision tree that works across the board for all possible situations in all cities, in all states. In that case, if we want to really make the general tree applicable to every situation, then putting restaurant name as the attribute will make the decision tree maybe shorter but naive, not generalizable. The example data looks like this. So we have 12 examples. The target variable is will weight, and true is represented by green dot and false is represented by. The thing is that XOR and OR are not the real problems that we are going to try to learn from the data. They are just examples of truth tables that we can look at to see how the decision tree can be represented if everything is binary. In reality, we don't have binary. We have multiple values in each attribute. But to keep things the simplest way, let's assume attributes are binary, dependent variable is binary, and we want to learn, let's say, for 10 attributes, there will be 2 raised to power 10 rows required to represent the complete truth table, and 2 raised to power 2 raised to power 10 row examples will be required to create that mapping between dependent variable and 10 independent variables, which is too much to ask. We never have that luxury. So look at these. If we have 10 variables and output is binary, this many rows and this many examples, we need to construct the complete truth table. And that, number one, we don't have that much data, never have that much data. We have only example or sample data. It's okay, having truth tables and everything is okay, but even for 6 attributes, we are looking at this many possible trees to solve an arbitrary problem, which is, I mean, if we need to go through this many trees and check which one works best, it's going to be a serious bottleneck, right? We don't have only 6 attributes sometimes. Mostly we are working with the hundreds of thousands of attributes. So we need some way to measure which of the attributes is most beneficial for given problem and do this induction of decision tree through the data heuristically. So there is, for sure, the full scale of the problem is humongous. And if some heuristic can help us out, even if the solution is suboptimal, it will be better than looking at this many trees to find out which one works best for only 6 attributes, and that too binary, right? So the main goal is that given the training data, if we can produce a plausible tree that agrees with the data, then we are happy with that. It won't be optimal, but there are ways to. One way is to have a humongous number of possible trees and compare and find out the best one. The second way, if our goal is changed, instead of finding the best tree, we restrict ourselves to find a good tree that confirms with the training data or the example data. In that case, our option, naive option, can be that we create one branch of the tree for every example. For every example, there is one branch of the tree. So if there are 12 examples, there will be 12 branches, and that tree will be consistent. But there is a problem with that because the example data is something that happened in the past. We don't know what comes in future. If we create a separate branch of the tree, then it won't work with future data. It won't generalize. That's why we need to have another way. We want a compact, concise, representative tree, but not one branch for one example, but as well as not so simple that it doesn't work at all. Finding that balance is NP hard. We need a solution that somehow gives us the simplest explanation of the problem that we are trying to learn. Our algorithm should find the function between x and y in simplest possible way, but not simpler. And then we induce that tree through heuristic or greedy search approach. And that approach is we are going to look at a new keyword here based on information gain. There are other statistical measures related to information gain term that we will learn, but for now, let's focus on information gain. What is it? So given the pattern attribute, we see that patterns attribute have three values, none, some, and full. And the dependent variable is giving us half and half of examples for will wait and will not wait. So somehow we will see that the decision tree that comes out of this data, the patterns become root node of the tree. And obviously, we want to have the root node some attribute that has most explanatory power about dependent variable that can classify the best in a given set of attributes. So look at the patterns. We can see that pattern is classifying into the sum value is classifying clearly to will wait, none value is classifying clearly to not wait, and full is a little bit confused. However, type of the restaurant is fully confused. So French, Italian, Thai, or burger for all types of restaurants, customer is either waiting or not waiting, 50-50 distribution. So given these two attributes, we will tend to choose patterns because it splits the data better than the type. Now, the type, if we use type, it will be useless to keep it in the tree because it's not helping us to decide which class the example belongs to. It will just delay the decision to the next node. So keeping type in the tree is going to be expensive in terms of time, memory, and processing. So let's look at the mathematical details. How do we pick up the nodes? We want to determine which attribute in the given set of nodes is most useful, and that will be based on the information gain metric. The higher the information gain, the higher the position of the node in the decision tree. It comes out of two submatrices. Entropy of the parent node. Don't get scared by the word entropy. I will explain what is it. And entropy of the child nodes. So in here, just remember these two boxes. We will fit some equations in these two boxes and they will make sense shortly. Let's first look at the entropy. What is entropy? Is information theory term that is defined as number of bits to transmit a piece of information. So for a variable that can have two values, we need 1 bit. Just like that. So entropy is in the context of decision tree, homogeneity or heterogeneity, purity or impurity of a set of examples. In this set, we have 7 red and 7 blue examples. So the information content that we can learn from this bucket is entropy of this bucket, attribute, or variable. So on the left-hand side, the attribute or variable or this bucket has all red examples, so we learn nothing. If we use this attribute, we will learn nothing about the dependent variable, which is the type of the ball. If we randomly pick a ball out of this bucket, we are 100% sure it's going to be red. On the right-hand side, It is maximum impure data set, 7 red, 7 blue. And it's because it provides maximum entropy, it is good training set for learning. How do we calculate mathematically? We just look at number of examples, total T, positive P, negative N, and then when we put them in this formula, so summation of P over T and log base 2 of P over T, when we sum them up, the negative sign, then we get the entropy. It is the learning potential of a data set. For example, if there are 7 examples for negative, 7 for positive, entropy will be 1. If all examples belonging to one class, entropy will be 0. 9 examples for positive, 7 for negative will end up in 0.94 entropy. We can map this to this curve. On the x-axis, we have proportion of positive examples in the set. All positive entropy will be 0. All negative entropy will be 0. And in between, it will increase up to 1 and then decrease. Due to the definition of entropy, we can say that entropy of an attribute P will be equal to entropy of 1 minus P, given that the variable is binary. Now, how do we fit entropy into the equation of information gain? Information gain is the grading mechanism. How do we grade different attributes? So given an attribute A, we calculate information gain in terms of the entropy of the node that we are dealing with, parent node in the decision tree, and the child node's expected entropy. I will explain what is expected entropy. Take an example of this node that in the tree, we can call it parent because it's parent of these child nodes. The expected entropy will be for positive and negative examples. If we sum them, the entropy of each child, then this is going to be the expected entropy of E minus expected entropy from the entropy of the parent node. We get a number called information gain. This is all what it takes for the proposal of a famous decision tree induction algorithm proposed in mid-90s by Mr. Ross, ID3 algorithm, inducting dichotomous decision trees. This was the basic algorithm that was extended into many more sophisticated forms, but once we understand this ID3 algorithm based on information gain, the others come very easy. If we try to calculate information gain of X, how shall we do? The parent node is C. It has half and half distribution, half 1, half. So half and half means the entropy is maximum. Entropy of parent is 1. For the child nodes, if we decide to split on X, when the X value of X is 1, in that case, value of C is 1 2 times and 2 1 time. In this case, for child 1, the expected entropy is 0.9184. For child 2 0. When we add them up, the expected entropy for child nodes come down here, and one parent's entropy minus expected entropy of the child nodes give us 0.3112, which is information gain. If we decide to use X as our independent variable to decide value of C, then the information gain that we get from X is 0.3112. Remember, the maximum will be 1 and minimum will be 0. We try to use Y, the same numbers, expected entropy of pure node, entropy 0, pure node, entropy 0. We multiply by the weights, add them up, 0. So for parent, entropy is 1. So the best one attribute out of X, Y, Z looks like X, looks like Y, because the information gain we get is maximum. For Z, it's the worst case. It's totally confused. Child nodes are totally confused. So their entropy is 1, 1, and when we minus from the entropy of the parent, the information gain is 0. That's why now we get some feeling of how this formula makes sense and how it can be used to pick up the best attribute out of not 3 and not binary, out of any type of attributes, out of as many attributes as there are, we can pick the best one and we will make it the root of the tree. And then next one, and then next one. So you are getting the feeling of it, right? So for the decision tree example for will weight problem, we can calculate for the patterns, the parent node, the entropy is 1. The expected entropy for the none, sum, and full child nodes is like this. So 2 over 6 and 4 over 6, the entropy multiplied by the weight 6 over 12. When we add them up individually and minus from 1, we get 0.541. Comparatively, when we use type attribute, we get 0 information gain. You will just put these numbers in the equation, add for the child nodes. Don't take child node as a literal decision tree terminology. It's like my way of explaining in the tree, we have a parent node and the child nodes. So individual entropy of the child nodes weighted by the number of examples there are falling in that child node. When we add them up and subtract from the entropy of the parent node, we get information gain. It's a kind of layman way of remembering things. For type attribute, entropy 0. For patterns, entropy 0.54. Given these two, you will pick the one that gives you more information gain. So you are gaining more information about the dependent variable from patterns attribute compared to type attribute. So the decision tree that I showed published in the textbook was learned through an algorithm. I mentioned ID3, and ID3 has these 4 steps. First, pick each of the attribute one by one, calculate information gain, arrange the attributes in descending order. The best attribute will give you some examples, some decisions, where you keep those examples decided. So that part of the tree is deciding 10 out of 20 examples. Now, remaining 20 examples, you will again calculate information gain and rearrange the ordering of the remaining attributes and find out the best one until there is no more example that you need to classify. So you repeat this process, calculate information gain at the time 0 for all attributes, you pick the best one. And then next, that best one will give you a decision for, let's say, for patterns attribute is giving you decision for 6 examples, only 6 are remaining. So for these 6 examples, you will again calculate information gain for the remaining attributes and find the best one and put it under full. And then move on to the remaining examples until you get a tree that is consistent or better than the other trees. This is all there is about the ID3 algorithm. So in this example, the plot is showing a 2-dimensional data set where the question marks are our test data points, and we get to see only the color data points. And we want to classify the test data points into either of these 4 classes, blue, orange, red, and green. So in this particular decision tree, considered imaginary, we are trying to just see how it works in terms of the division of the data. So S naught is the first decision that we make here, which divides the data using this horizontal line. So above this line and below this line go right and left of this node. And then we draw another line, S1. And then we draw another line S2. So S1, S2 will split the data points into smaller and smaller buckets until we reach to the leaf node. So in the beginning, the probability for all four classes for a given data point, it's equal. But when we walk through a certain branch and reach to the leaf node, the probability for one of the classes rises above than the other classes, and we decide that the example that reached to this node is of red class. It's kind of another naive visualization of how we can look at what's going on inside the decision tree once it is learned. So on training time, we will use example data, these colored points, and induce this tree. Once the tree is learned, we will use these test points to classify them into one of the classes, one of the four classes. Now, visualizing information gain in this diagram, we see on the left-hand side, there are four classes. And class distribution shows that for every class, we have 20 data points out of 100, 20%. On the right-hand side in B, if we split the data using this horizontal line, we get a very confused decision. So splitting on this variable on the y-axis, variable that is on the y-axis, will give us an information gain that is not helping. If we calculate, it is 0.40. On the x-axis, if we split this visually, you can see it is separating classes in a good way. Now, the information gain is 0.69, better than 0.40, because on the left of the split point, we have only two classes. On the right, we have other two classes. So this decision point is solving half the problem. That's why the information gain is higher. So far, I think you are at least convinced that information gain will work in selection of the attributes. And once you select this attribute, they split things into two quite successfully, and the remaining attributes, which one to choose, you will again calculate information gain for the examples that could not be solved with the previous attribute. And you will move on until you exhaust all the examples and the attributes. Now, there will be very rare cases where you can learn a perfect, consistent decision tree through your examples. The leaf nodes will always be having some kind of confusion, and you will see that if we use all the examples, the training error reduces. But is it advisable? Is it practical to use all the examples? If we want our decision tree to work tomorrow on the future data, in that case, we need to split our data set into training and test. And we shouldn't use test data points or examples while training. Splitting into two has its own demerits. Maybe we get a lucky catch of having very easy test examples, and we become very happy that our decision tree is very good. But in practice, when we deploy it in future, it may produce bad results. So a better way of evaluating your decision tree, training of the decision tree, is using cross-validation. visualization will work better. So here we are splitting our data into three, and we are training three decision trees with different split of the data. This one is coming out of blue, this one is coming out of yellow, this one is coming out of red. So we are training with the one segment and evaluating with the other segment. It can be 5 split or 10-fold or 20-fold depending on the size of the data. So we use one fold to test and other folds to train, such that every data point gets a chance to be tested on the algorithm. So we will have 3 decision trees. If their performance is consistent, that means we are doing well. The algorithm is doing a good job on learning the function between independent variables and dependent variable. Sometimes we come across with this problem of peaking, where we look at the evaluation results and then go back and change the structure or the algorithm to learn the tree, and that is referred to as peaking. So that's why in practice, we never get to see the test data. It is kept as a future data that we don't have access to. We always get training data. We split it into n folds or k folds and use k-fold cross-validation, as I explained in the previous slide. Learning decision tree is one thing, but how to learn it in a good way, we need cross-validation. You're convinced why we need that, because we want to touch every data point, give a chance. We want to give the chance of being tested to every data point. So we do this cross-validation, and we avoid peeking into the data through test data to keep some part of the data as future, so we never know what is in the future. And how do we measure what is good, what is bad? We are going to learn many matrices, but in case of classification, we look at accuracy. In case of regression, we look at some kind of difference between actual and predicted value. There are many more interesting and relevant measures that we need to know. You will get that information in the modules as well. But these are the two basic ones, right? And decision trees, I provide some examples here. For example, in this comparison of decision tree with human experts, so they found out that decision trees provide on across different measures better performance for detecting some problems in ultrasound images. And a famous study of British Petroleum used the decision trees and replaced the expert system to detect oil, separate oil and water. And this study found decision trees do better than human trainers. Like autopilot is better than trainer for training how to take off and land. So many interesting applications. I just quoted 3. Now the thing is that on x-axis is the number of examples that we have in our training set. So the more examples we use in the restaurant data set, the better we have the performance. So few examples, we have more mistakes. The more the number of examples, the higher the performance is, accuracy or whatever we try to use. But this is not, as I explained, if we have 100 examples, this is not the best policy to use all to train our any algorithm, not only decision tree. If we use all examples, one big risk is that the algorithm will memorize training data and will give very good performance, but in future on test data, it will fail terribly. So this curve is used in textbooks to explain why the performance measured on y-axis in terms of accuracy and the size of the tree that if we use all the data, all the attributes in the data, the size will grow. So 10 nodes, 20, 30, up to 100 nodes. Up to 100 nodes means every example in the training data has a branch in the tree. So that will cause the accuracy to go up for training, but go down for test. And they diverge. The more the size of the tree, the bigger the difference between test and training will be. So we want to find a sweet spot where the tree is concise. It's not too much complicated. It's not using all of the examples and all of the attributes, but best possible and provides good enough accuracy and balance between test and training. Now, this is textbook, right? So we, in practice, never know where do this line go because we don't have access to the future data. That's why we split into train and test. And if we plot this error with respect to the decision tree, for most of the problems, you will see this divergence. And this is called the problem of overfitting. The higher the training error goes, the algorithm or the decision tree is memorizing, overfitting to the examples and becoming less and less generalizable for the test data. It's just like even if we add in some random attributes, for example here, to predict the result of the rolling a die, we add day of the week, month of the week, and color of the die, which has no correlation or no connection with the result of the die. If it's fair, then we put in these three variables and the decision tree can somehow learn, add these variables from the training examples and get misled. So in future, we know these don't have any implication on the result of the die, but they will be incorporated into the decision tree or any other algorithm, and we are set then for problems. So overfitting onto irrelevant variables is one cause of that divergence. And the next textbook graph for the same concept that I want to show you. On x-axis, we have size of the tree, number of nodes in a tree, and on y-axis, we have error rate. The higher the size of the tree is, the lower the training set. And at some point, we see that the error starts increasing for test set, and we want to touch that sweet spot somehow. Optimal tree size, maybe 6 or 7 nodes. Less than that, we are underfit. Beyond that point, we are overfit. Now, other than these irrelevant variables and size of the tree or number of examples that we use to induce a tree, there can be some problems that we want to avoid. For example, one problem is same example in both classes. Noisy data, right? Same example, all attributes, same values, class 1, same values for class 2. That is not possible, right? That must be an error, noisy data. But if we keep increasing the size of the tree and keep feeding all the examples to the data, as many as we have, the tree will get overfit to those examples and produce erroneous results in future. Similarly, there can be noise in the attribute values as well. Not only the confusion between the class labels, but the attribute values can be recorded incorrectly. So accepting the fact that there will be noise in the data, we don't want to train too much, too long, using all the information we have, increase the tree size as much as possible. It's a guaranteed way to overfit. So that's why avoiding overfitting has many reasons: to avoid the noisy data, to avoid the mislabeling problem, and to have a concise hypothesis, not too big, not too small. So in conclusion, when the instances can be represented into attribute value pairs, we are good to choose decision tree. It is mostly if the dependent variable is having discrete values, decision tree is a good option. But if it is having numeric values, continuous variable, we can still use decision tree. We refer to those decision trees as regression trees. And concise term is CART, classification and regression trees. Whatever is the dependent variable, decision tree will work. But I will leave it to your imagination how a classification tree can solve regression problem. You just need to think about the leaf node. In the leaf node, in classification, we are getting discrete items. But in regression problem, the leaf node will have a range of numbers. And we can take an average of those numbers and output the average as regression output, or we can fit a regression inside the leaf, regression solution inside the leaf node for all the data points, and use that regression solution to output Y. So it's robust to noisy data, and we use in machine learning a term Occam's razor. That means we don't use a more complex representation to explain or communicate a concept that can be communicated with simpler representation. The first thing that you do to solve a problem, classification problem, is a decision tree, because it does outperform human experts, and it is fast to build. It is simple to implement, like to deploy on the cloud, and it's human readable. So you induce a decision tree, and then a domain expert can verify, yes, this decision tree is according to the complexity of the problem, and the variables and decision variables are having good decision factors. And even in newspapers, you often see decision trees being published for common people. And they are being used in many commercial products, and they do have some downsides. Number one, each node will handle one variable at a time. We live in a multivariate world, right? So this is one limitation, too naive for the real complex problems. And large decision trees can be produced, and they will be hard to understand by us. And finally, for a decision tree, for learning a decision tree, we need to have a data that is of tabular shape structure. So fixed length feature vectors is the prerequisite, and we have to have all the data. Only then we can learn. We will see some problems where we can apply algorithms that learn on the fly. As the examples come, we update the algorithm, and it learns incrementally, stochastically. The decision tree is a batch mode learning method where we need to have all the data first in place, and then we learn. If new data comes in, we will create a new tree. The old one will be discarded.